I'm David Miller of Stanford University. Silicon photonics lets us make complex optical circuits, including quite sophisticated meshes of interferometers, for example. There are many interesting things we could do with such meshes. In fact, they offer a kind of universal linear optics well beyond conventional optical systems. Now, to use these meshes, we need to control them. But with large numbers of interferometers, calibration, configuration, and stabilization is hard. No one wants to line up 100 interconnected interferometers. But that is where self-configuring photonics comes in. Specific architectures can correct, stabilize, and configure themselves using simple, progressive algorithms with local single-parameter feedback loops, and they can adapt to the problem in real time. Meshes like these have various applications. They give optical systems that are universal in a way that is quite beyond previous optics. They open new opportunities in sensing, in communications, and in information processing. For example, neural networks, solving equations, and this is true for both classical and quantum systems. To understand how these self-configuring architectures work, we can start by looking at the simplest of them, which is a self-aligning beam coupler. This is going to take a set of mutually coherent inputs in different waveguides and automatically combine them into one output. To start, we should remind ourselves how we null out a port in an interferometer. Consider a waveguide Mach-Zehnder interferometer, formed from two 50-50 beam splitters, that is, equal beam splitters, and at least two phase shifters, one phi to control the relative phase of the two inputs, and a second theta to control the relative phase on the interferometer arms. Suppose we shine mutually coherent light into both interferometer inputs, with possibly different amplitudes and phases. We can adjust phi to minimize the power at, say, the bottom output. The fields from the two inputs are now in antiphase, they're in opposite phase at the bottom output. Adjusting theta sets the split ratio of the Mach-Zehnder, that is, how the power from one input would be split between the outputs. Interestingly, for 50-50 beam splitters, adjusting theta does not change the relative phase with which the two inputs mix at an output. That is controlled only by phi. So, since we have already minimized the bottom output power by adjusting phi, if we now adjust theta, we will be able to minimize that power to 0, because the contributions from the two inputs are already in antiphase at the bottom output, and it's always possible, therefore, to find some ratio of these two contributions that is exactly equal and opposite. So, in a Mach-Zehnder with 50-50 beam splitters, for any relative input amplitudes and phases, we can null out the power at the bottom output by two successive single-parameter power minimizations, first using phi and second using theta. In fact, in making meshes of Mach-Zehenders, we can use Mach-Zehnder blocks with phase shifters in any two of these four locations, as long as at least one phase shifter is on an interferometer arm. It is incidentally possible to do this using both phase shifters being on interferometer arms. The algorithm is slightly different then, but this still works. Now we can take the next step, which is to combine multiple interferometers, for example, in a chain or diagonal line. We will progressively null them, one after the other, until we are left with all the power in only one output. Note, incidentally, we are going to do this without calibrating anything and without performing any calculations at all. So here we have a diagonal line of three Mach-Zehenders, one here, and one here. We have four input waveguides with light shining into each one of them, all mutually coherent, and we have one waveguide at the right where we hope to look for the output. We also have three detectors here. So we start by minimizing the power in detector D1, this one here, by adjusting the corresponding phi and then the corresponding theta. Putting all the power now in the upper output of this Mach-Zehnder. And that changes the power in the output at the far right at the top. Then we minimize the power in detector D2, that's this one here, by adjusting the corresponding phi and the corresponding theta, again to put all the power in the upper output now of this Mach-Zehnder, which also changes the power at the top right. Finally, we minimize the power in detector D3, this one here, by adjusting the corresponding phi and then the corresponding theta to put all the power, now the total input power, in the upper output. So we could, for example, have grating couplers that couple some free space beam shining onto the top of this chip on the right here to a set of waveguides. Then, using our algorithm, we could automatically couple all the power from those grating couplers to the one output guide on the top right. This could run continuously, tracking changes in the beam and still putting all the power in the output. In addition to the diagonal line, a binary tree of Mach-Zehnders, as shown here, also supports self-alignment. It uses the same number of Mach-Zehnders in each path, which can be a minor advantage, and it is also the shortest possible self-aligning coupler mesh. Now, each column of the Mach-Zehnders can also be optimized in parallel, allowing faster self-configuration. So both of the Mach-Zehnders in this column 1 could undergo optimization or minimization at the same time, and then we could proceed to the next column. And this continues to work as we make more complex sets of binary tree meshes. Once we have aligned beam 1 to output 1 using detectors D11 to D13, that is, these detectors here working with this diagonal line of Mach-Zehnders, an orthogonal input beam, 2, would pass entirely into the detectors D11 to D13. None of it would appear at the output. That is, if at the input, instead of the vector of amplitudes we originally shone in, that we used to align all of that power to this output, if we shone in a vector of amplitudes that was mathematically orthogonal to the first one, none of it would appear out here. And indeed, if it did, it would violate the second law of thermodynamics. So all of the power in this second beam now will actually pass into these detectors. If we make these detectors mostly transparent, all of this second beam would actually pass into the second diagonal row. That is, this diagonal row of Mach-Zehnders, where we could self-align it to output 2 using power minimization in these two detectors. This would separate two overlapping orthogonal beams to separate outputs, which actually is something that we really did not know how to do before. So here is exactly this kind of system that can separate two light beams. In this case, we have a square array of grating couplers here that are going to receive the incoming light beam. So those are here on the actual chip, or magnified as we see here. Then there are two diagonal lines of Mach-Zehnders, and these can separate two orthogonal patterns on here to two different waveguides at the output here. And the experiment in this case is to shine, first of all, a simple light beam, a single bumped light beam in here, and have that come out one of the waveguides. And here we're shining a two bumped light beam. We've changed the phase between the two halves of the light beam, so it's now orthogonal to this one, and we can separate it out to the second waveguide. And this can all be accomplished automatically by self-configuration of this system. And the beams are entirely overlapping on these grating couplers. Adding more rows and self-alignments separates a number of orthogonal beams equal to the number of beam segments, here 4, the 4 waveguides. Note, incidentally, it's possible to set this up with only detectors at the outputs instead of these embedded detectors, though then we may need to tear down the network to reconfigure it. But we could still run with only detectors at the outputs to perform this kind of self-configuration. If we now put identifying tones on each orthogonal input beam, that is a small modulation at some frequency, for example, and we have the corresponding diagonal row of detectors look just for that tone, then the mesh can continually adapt to the orthogonal inputs, even when they are all present at the same time, and even if they change. And this is exactly what my colleagues at the Politecnico di Milano did. They took 4 separate fibre inputs and combined them in a multimode mixer so that when they came out, they were completely mixed up. But they had put identifying tones on each of these input fibres, and by using those tones to pull out specific inputs when configuring using these detectors, they were able to separate out all of the beams again, even though they were completely mixed here. And incidentally, if they changed the multimode mixing here by heating up this multimode mixer, the system would reconfigure automatically to separate the beams out again. So we are starting to see that these kinds of meshes can do things we could not do before in optics, including adapting in real time in important problems. This is really a new opportunity, and we're only just now starting to exploit it. Let's see what other kinds of things we can do. But what if the Mach-Zehnder interferometers are not perfect? In particular, the split ratio in the beam splitters may not be 50-50. Without 50-50 split ratio in the beam splitters, we cannot in general get perfect cancellation at the outputs. And that limits the functionality. However, there is an algorithm for adjusting the split ratios after fabrication, based only on maximizing or minimizing power in detectors. And that can set both beam splitters to 50-50 after initial fabrication. Importantly, this does not require any calibrated components or balanced detectors to equalize powers. If we use Mach-Zehenders themselves as effective variable beam splitters, the fixed fabricated split ratios in those beam splitters can be as bad as 85-15, and we can still perfect the overall system. With colleagues at the University of Bristol, using our algorithm to adjust the effective beam splitter ratios, we can indeed improve the rejection ratio from -30 decibels to -60 decibels in this Mach-Zehnder system here. So we have one Mach-Zehnder functioning as a beam splitter, another Mach-Zehnder functioning as a beam splitter, and we can correct for the fact that the fabricated split ratios in these various couplers here are not actually 50-50. No calibration or calculations are required for this, and this is based only on power minimization or maximization in an output detector. Now let's look at another application, which is analyzing multimode fields. Suppose we have a field with amplitudes in various different modes. How do we analyze that automatically? There are various ways to separate modes, which could give us the relative magnitudes in the modes, but how would we get the relative phases? We could interfere with a coherent reference beam and perform some additional calculations, but we may not have such a beam. For example, if we're looking at a remote source, or one that is of broadband or of limited coherence. Here we show how we can do this without a coherent reference beam. And to do this, we repurpose our self-aligning beam coupler, which can perform all of the relevant interferences between all of the parts of the beam. If we shine in the beam into this example optical input set of grating couplers here, for example, and have this mesh network self-aligned so all the power appears at the output, then from the settings of the phase shifters in the mesh, we can simply deduce all of the relative amplitudes and phases of the inputs. Also, we can run this backwards to generate an arbitrary multimode field. In this case, we would shine light backwards into the output waveguide, and we would be able to controllably generate any desired multimode field backwards on the left. Here is an example of generating exactly the right beam that we want. In this case, we have a diagonal line of Mach-Zehenders, so it can generate an arbitrary set of 4 complex amplitudes, or amplitudes and phases, coming out of 4 grating couplers here. And in this case, we're looking in free space, for example, in the far field. Here's a picture of the circuit. And what we're doing first of all then is we are optimizing this mesh to maximize the amount of light in the center of the camera. So in this case here, we see a nice bright line. So we've chosen these by optimization to maximize the power in the camera. Then we introduce a diffusing mask. So in this case, it's a diffusing medium here on a silica substrate, and that's introduced into the middle of this path. And you can see that as a result, the pattern on the camera is now quite changed. In particular, there is not a bright line in the middle of the camera field. Then we re-optimize the settings in the mesh, again to maximize the signal in the middle of the camera, and sure enough, here it is. So the mesh is now pre-compensating for the distortions introduced by this phase mask in the middle, or as shown larger over here. Quite generally, we can use a self-aligning beam coupler as what we could call an optical setup machine. That is, a system that can essentially calibrate itself and can be used in reverse to controllably generate arbitrary multimode fields. We can use such an optical setup machine to calibrate and set up other arbitrary forward optical mesh circuits, including ones that are not self-configuring, such as lattice filters and rectangular or hexagonal meshes. The key trick is to imagine running the desired network backwards with imaginary light shone into just one port of a Mach-Zehnder interferometer. This is called the reversed local light interference method, and it's given in this paper. We can also parallelize this approach. Generally, a forward-only network can be reorganized into columns while retaining the same topology. So here we have topologically managed to identify what we can think of as columns, and we can regularize those into these columns we've shown here. The key point about this regularization is that all of the items in a given column can be set in parallel in the same time step because they don't influence one another. And there's a topological algorithm we can go through to complete this identification into columns. And hence we can parallelize the setup of complex forward networks. And this reduces configuration time. So far we've talked about some specific potential applications, but another important point about these meshes is they can be quite universal as well as self-configuring. Universal architectures, for example based on concepts like singular value decomposition, allow any matrix multiplication. So for arbitrary linear optics, for neural networks, and neural networks have used these architectures, and for classical or quantum processing. And as I said, these networks can also be self-configured while still being universal. And hence they offer universal field programmable linear arrays. In this architecture, the self-aligning input coupler mesh on the left, so this one, can couple any 4 orthogonal inputs to these single waveguides in the middle. So one orthogonal input goes here, a second here, a third here, and a fourth here, and so on. Light in those single waveguides can be converted into another set of 4 orthogonal outputs on the right, any set we like of orthogonal outputs here, using this mesh on the right. The amplitude and phase of this conversion can be controlled by the line of modulators in the middle. This kind of universal mode conversion with such modulation corresponds to being able to implement an arbitrary and non-unitary matrix from the inputs to the outputs, at least if we do not require gain. If we do require gain, we can add gain in the middle here. So this mesh is fully universal for performing any linear transformation from the inputs on the left to the outputs on the right. The mathematical reason why this works is because we can always perform the singular value decomposition of a matrix. That is, we can always write a matrix in the form of a product of 3 matrices, a unitary one, a diagonal one, and another unitary one. The optical units in this mesh implement the singular value decomposition. Here is the matrix U dagger, a unitary matrix. Here is the diagonal matrix, and here is the second unitary matrix, V. This, incidentally, is the first proof that any linear optical component is possible. And incidentally also that any linear optical system can be factored into a set of two-beam interferences, which is something that may not have been obvious to you. This can be used in thought experiments for fundamental proofs as well. We can also flip this logic around. We can always perform the singular value decomposition of any linear optical component or system. So any linear optical system can be described as a mode converter. And these sets of modes that we come up with turn out to have basic physical significance. When we think of how some source function, which we'll write here in a Dirac notation, psi s, in some source space, so as we see here, some hypothetical source function, for example some currents inside some source volume, gives rise to a received wave, which we'll call phi r, in a receiving space. For free space communications, or for any scatterer, optical device, or object between the spaces, there is just some linear operator, d, that relates the two. That is, we imagine there's something in here, it could just be free space, or some device, or some scatterer, and sources in here going through this give us waves over there. And we can describe that with just a linear operator. So mathematically we can write that in this form. The simplest way to think of this is a vector of amplitudes, for example at points in space. This is the coupling operator, and this is the resulting wave, which we can also think of as a vector of amplitudes, in which case we can also think of this as a matrix, for example. Because we can perform the singular value decomposition of any linear operator d, we can have what we can call the mode converter basis sets of functions. And this is an idea that was introduced in 2012. That is, a set of orthogonal source functions, so a whole set here for different j's in the source space, that lead one by one to a set of corresponding orthogonal received waves, so phi r, with also this index j here. In turn, that means that there is a set of orthogonal channels for communication through space, or even through a device or scatterer, which are given by these mode converter input and output function pairs. These are the unique and best possible choices. For any linear optical system then, singular value decomposition gives an optimal orthogonal set of input functions that map one by one to an optimal orthogonal set of output functions. These allow a rigorous, what we can call communications mode, counting of communications channels, including the conclusion that there is always only a finite number of usable channels, and including specific new limits for various optical systems. And we've derived all this in this paper here. It also gives a general form of diffraction theory, valid for all sizes and shapes of objects. It gives the most economical, what we can call mode converter basis description of any linear optics. It allows us to derive new laws, such as new versions of Kirchhoff's radiation laws, valid for all objects, and that includes nanophotonics and non-reciprocal systems, which was not the case for previous Kirchhoff radiation laws. And it allows different quantum mechanical results, for example, a new mode-by-mode version of Einstein's famous A and B coefficient argument that explains spontaneous and stimulated emission and absorption. And it also even allows a new quantization of the radiation field in any volume. So, in conclusion, I hope I've shown you that self-configuring photonics enables complex circuits for new optics. The algorithms to calibrate and use these circuits are simple and fast, and we are just beginning to understand the many uses of these ideas. I'm very pleased to acknowledge my funding from the Air Force Office of Scientific Research, and if you would like a copy of the view graphs in this talk, please just send me an email. I'll finish by putting up some of the references in this work. Thank you.